maybe even a little bit early. We'll see how that goes. But my afternoon schedule's a bit bunched up with meetings. Talk.
I think it's something that got,
Well, hopefully they're not like little nubs.
and there was a box in that board.
Oh, okay. Okay, we got some good side pages here. Where we get these just standard that would be a full box in the wall, full of fresh pieces of long pieces of chalk. Like, yep. Schools are resources, schools are not resources. Okay. So all along, this chapter is focusing on finding all the eigenvalues of an n by n matrix without any assumptions. But of particular interest is the case where the matrix is, they were taking real matrices, if the matrix is symmetric. Okay. A lot of things simplify, but certainly symmetric matrices are important in a number of applications. So it's simplification worth knowing about. Okay, so when all eigenvalues such as f equals lambda x, A is a real symmetric matrix. Okay. Now, we have a short decomposition. A equals QT Q transpose. So now I'm going to transpose both sides. So A transpose is going to be Q T transpose Q transpose. It's a transpose of a product. It's a product of a transposes in reverse order. That equals A because A is symmetric. So if you multiply both sides of this equation on the left by Q transpose and on the right by Q, let's do, and you do the same thing for this equation. You want to both are equal to A. Then we have T transpose is equal to T. So since A is symmetric, the T matrix from short decomposition has to also be symmetric. But then T is upper triangular. And I'm saying that a transpose of an upper triangular matrix, which is lower triangular, this is saying lower triangular equals something that's upper triangular. So what can we conclude about T? What kind of matrix is it?
That has to be upper triangular, but yeah.
Well, if it's both triangulars.
Then it's symmetric. Well,
it is symmetric, but diagonal.
Yeah.
Yes.
Just be the diagonal entry.
Yeah, so T is diagonal. Okay. Okay. So, so what we can say is, A is unitarily diagonalizable. Now, I'm focusing on the case where A is real, but I can extend this a little bit. So if A is real, we have A is equal to Q D Q transpose, where Q transpose Q's identity. So we say that Q is orthogonal in that case. Oh, I'm sorry, A is real and symmetric. Okay. All right, so we have that. But I can make a similar statement in the case of A is complex. A is equal to a Hermitian transpose, or AH. So I'll say A is equal to QD QH. QHQ is identity. So we say that Q is unitary. In that case. All right. So A is diagonalizable, and that's something we did not always have in the unsymmetric case. We saw that some unsymmetric matrices cannot be diagonalized, but any symmetric matrix can be. Okay. Okay. I can make a somewhat stronger statement in this. This also holds that's unitarily diagonalizable if A is normal. Meaning that A commutes with its own Hermitian transpose. For example, if A is a skew symmetric matrix, so A is equal to minus A transpose, that also works. Now, something more we could say is, okay. Follow this. So a complex case T is also equal to its own Hermitian transpose. Okay. Right, so I'm going to return stick with A being real. So now I can say, by rearranging this equation over here, AQ is equal to QD. So I'm multiplying both sides on the right by Q. And if I let Q have this column partition, and orthonormal columns, then if I look at this equation one column at a time, I have A QJ is equal to lambda J QJ. So the short decomposition tells us a lot more about A's eigensystem in the symmetric case than it does in the general case. So, because remember I described the columns of Q, where Q is a matrix, the orthogonal matrix from a short decomposition, as Shor vectors. All right, so these are Shor vectors still, but we can also say that they are the eigenvectors. I mentioned at the end of last time, after driving the QR algorithm, the Francis QR step, all that, like, okay, now we see how to get the eigenvalues and the real Shor form. But I did not get into how to get the eigenvectors in that case. It's not easy. That'll take at least a whole other class period to cover. But in the symmetric case, if you carry out the QR algorithm, you get the real Shor form, then you get the eigenvectors for free. For just your Shor vectors. I mean, there's still additional significant additional expense on top of getting eigenvalues, but it's still a lot less than the unsymmetric case where you'd have to do even more beyond what I described. Okay, so, all right, so we have this diagonalization. Okay. Now, suppose I take the equation I just wrote down, AQJ lambda J QJ. If I take the dot product of both sides with QJ, okay. That's one, because it's QJ, it's for kind of an orthonormal set of vectors, so dot product of itself is one. So lambda J is equal to this. But this expression here, A is a real symmetric matrix. The Q's are QJs are columns of a real orthogonal matrix. So, what we have here is, this is real. So we can conclude that the eigenvalues are real. So in general, a real matrix can have complex eigenvalues if they're in complex conjugate pairs. But if A is symmetric, a real symmetric, then the eigenvalues are actually real. Okay. A is complex, but is equal to is a Hermitian matrix, so A equals AH. Also, the eigenvalues are real. So in that case, the matrix A can still be complex, but if it's equal to its own Hermitian transpose, the eigenvalues are real anyway. It just occurred to me that I was a little bit sloppy here. And the reason I say that is, okay, so if we think about surety composition in general, A is equal to, QT, QH. When A is either real or complex. When you have B, and we also have a real short form. If A is real, then we have A is equal to QT, Q transpose, where T is not, as I mentioned, not upper triangular necessarily. It could have 1 by 1 or 2 by 2 diagonal blocks. But everything done here when I talk about real case versus complex case. I don't think I ever proved that in the surety composition where you have and I don't mean the real short form, but just the true surety composition. A is equal to QTQH, where T really is upper triangular and might be complex. I don't know if I ever proved. I don't think I ever proved that there exists a Q matrix in that case that's actually real and orthogonal. Now in the notes, I don't make the assumption that A is real. I say A equals AH, A can be real or complex. So you have this, the matrix in the middle, I call T before. Since A is Hermitian, T must be Hermitian. Because T is upper triangular and Hermitian, it must be diagonal. So all of that still applies, whether A is real or complex, as long as A is equal to AH. And then, okay, so that A is diagonalizable, all of that still applies. And then what I do in the notes is I look at this equation, the case again where A is either real or complex, and take the inner product with QJ. And I show that this is real. Therefore, the eigenvalue must be real. So it all works whether A is or whether A is real and equal to its own transpose, or A is Hermitian complex and equal to its own Hermitian transpose. But the eigenvalues are real. But in retrospect, to be more rigorous, I should have stuck with the complex case. And then you get that and you get the inclusion that language is real. But anyway, the eigenvalues are real. So but yeah, what I've done here relies on the assumption. Actually, you know what? Okay. No, because I feel like I've written something that's not rigorous enough, but it turns out there is an easy way to fix it. Okay. So I have. All right, it's best if I do not make the assumption that Q is real or orthogonal. So we have, where it's real or complex, we have the unitary matrix, no matter what. Okay. So then all of this still works. And then I go over here and I use a Hermitian transpose for my inner product because I allow for the possibility that Q's might be complex. This is still 1. And now I just have a little more work to do to show why, even if the QJs are complex, this is still real. Because, okay, so if I take this equation right here, lambda J is equal to that. And now I take the complex conjugate of both sides. Lambda J conjugate is equal to, well, when you take the complex conjugate of a number, that's the same as taking the Hermitian transpose of a 1-by-1 matrix. So I would have Q, J, H, A, Q, J, H. That's equal to Q, J, A, H, Q, J. All right. But AH equals A. Because it's Hermitian or symmetric if it's real. That's lambda J. So lambda J is equal to its own complex conjugate. So the conclusion is lambda J is real. Okay. All right. So I do not have to assume that the eigenvectors are real, but the eigenvalues are. Okay. Sorry if that digression all sounds like, oh my God, I was imprecise. Okay. Way too slow to this for my notes. Oh, God. Okay, get through this. Okay, so we have, the eigenvalues are real, so they can be ordered. But I'm going to assume that the lambda one, of course, is the largest, but now I don't assume it's largest in absolute value, it's just the largest. So, and it'll still use the same convention that the largest we refer to as lambda one and lambda two, and so on. Okay, you're gonna make a choice to skip some things just because of time, but also, it'll feature in the homework either. Like, as far as perturbation theory, I mentioned the Gershgorn circle theorem. The eigenvalues are contained with the union of the Gershgorn disks. That still applies here, except because the eigenvalues are known to be real. You don't have Gershgorn disks in a complex plane anymore. You have Gershgorn intervals. Okay. All right. But what I want to focus on is algorithms for computing eigenvalues in a symmetric case. Now we have a QR algorithm adapted to the symmetric case. That's focus on that a bit. But first, I want to mention the variant of the power method for finding individual eigenvalues called Rayleigh quotient iteration. Okay. Okay. So, so it's based on something I mentioned last time, I believe, inverse iteration. So an inverse iteration is the power method applied to a shift of a inverse. Okay, so now what that does is, as I mentioned last time, find the eigenvalue closest to mu. Because the eigenvalues of A minus mu I inverse are 1 over lambda 1 minus mu. If lambda is the closest to mu, that denominator is going to be smallest, therefore making the whole fraction the largest. Now, I should mention the power method is convergence rate. Now, I brought that up when I first covered the power method. So it's given by lambda 2 over lambda 1, so second largest over the largest in the general case. So general unsymmetric A. But it turns out that if A is symmetric, the convergence rate is squared. So power method, when it does converge, converges much more rapidly than for an unsymmetric matrix that has the same real eigenvalues. So right off the bat, you have an advantage there. But it turns out that by working with inverse iteration, we could get even faster convergence than this. So certainly if we use a shift, we could get an advantage. So what if we vary the shift when doing inverse iteration? And that leads to this still pretty short algorithm here. This is what really quotient iteration is. Or RQI, really quotient iteration. Okay. So what we have is we choose initial guess, call it X naught. Make it a unit vector. And then in a loop that will run until convergence. And we set our shift equal to a Rayleigh quotient of A and vector xk that we have, so initially x0. And that's why we need each xk to be a unit vector. Because normally for Rayleigh quotient, I'd have a denominator xk transpose xk, but that's equal to 1, which is why I didn't include it the first time. Okay. So hopefully this is an approximate eigenvalue. So then what I do to get my next guess at an eigenvector is we solve A minus UK identity times ZK equal to XK. So XK is the right-hand side. ZK is our solution. So in other words, we've formed one iteration of inverse iteration with mu k as the shift. And then I get my next X vector just by normalizing. K plus 1 is equal to ZK over its norm. Okay. And that's it. So the idea is the shift mu k is getting closer and closer to an eigenvalue because presumably ZK is getting closer and closer to an eigenvector as an output of inverse iteration. And because we keep updating the shift, this matrix is getting closer and closer to singular. And we're getting closer to that one eigenvalue that's closest to our shifts even more rapidly than if we just stuck with power method or inverse iteration with a fixed shift. And it can be shown that this iteration converges cubically. We don't see that very often, and we've seen cases of quadratic convergence with various topics, but you hardly ever see cubic. So if quadratic convergence means you only have to perform like maybe 5 iterations or so, but cubic you can get it over really quickly. Because unfortunately we do have the expense of solving this system, which is unfortunate. So each iteration is kind of costly, especially if A is not sparse. But we only have to do it very few times.
So for cubically, that means every iteration we're adding approximately 4 zeros to our error.
Or the number of correct digits is tripling.
Okay.
So 1, 3, 9. So yeah, 4 iterations, you're done. On average. Now, what you could do if you want to find all the eigenvectors, what you could do, I guess, is go ahead and use this to find n eigenvalue eigenvector pair. Because so mu k will converge to an eigenvalue, xk will converge to its corresponding eigenvector. So what you could do is then go back and run this again, where you choose your initial guess to be orthogonal to any eigenvectors you've already found, and then try to find more eigenvalues. But because of round off error, that's not really the most reliable approach if you want to find a lot of eigenvectors. So a rule of thumb is use either inverse or Rayleigh quotient iteration if all you want is like less than 25% of all the eigenvectors. So these kind of iterations are good when you want to select eigenvalues and eigenvectors. And you can choose a shift, like your initial, like you can choose your initial shift if you want to target finding like is equal to smallest or the largest.
Well, since we're starting with like lambda 1, if we use this, we can use this if we just wanted to find the 25% of the largest eigenvalues. This would find us the larger eigenvalues. Correct?
Well, but you have to be careful with your shifts. Like here, this shift is determined by your initial guess. So the thing is, if you're going to use this to find different eigenpairs, you need different initial guesses. Yeah. So that's one thing you have to be careful about. Now, what you could do here, I let the first shift be chosen determined by my initial guess. Now, if I don't really know what initial guess I want to choose, I could choose an initial shift. And then, so even if this, my shift has nothing to do with this, then at least my Z0 will be biased towards that shift. Maybe what I could do, and I actually had a master's student do something along these lines, where I had the shifts prescribed up to a point. Like, suppose you really do want the largest, then go ahead and choose a large initial shift. And if it starts to, once it starts to show signs of convergence, then maybe let this take over. So there's ways to skew it. Alrighty. All right. Oh, yeah. So I have a comment here about Rayleigh quotient iteration because it converges so rapidly. In practice, often a single iteration is sufficient. Like, dang. Okay. All right, so that's Rayleigh quotient iteration. During the rest of the time, I want to focus on revisiting the QR algorithm, but now how it's changed for the case of symmetric matrix. So it's a second and only other algorithm we'll look at. Symmetric QR algorithm. And for those of you who choose the coding option for homework 4, this is what you're implementing. Now, as we saw, the very first step in the QR algorithm is the Hessenberg reduction. So we go ahead and do that again. Well, the Hermitian transpose of H is going to be equal to H. So since it's A's, or okay, since A is symmetric, that's kind of weird to say H equals H. But we're assuming real matrices now. So a symmetric Hessenberg matrix is tridiagonal because in H, all entries below the first subdiagonal have to be 0. But by symmetry, all entries above the first superdiagonal also have to be 0. So that's something that helps a great deal. That actually makes the symmetric QR algorithm a whole lot faster than its unsymmetric counterpart. you still have similar expense for the reduction itself. But, okay. All right. And some optimization is possible, but still an order n cube job to perform the now tri-diagonal reduction instead of Hessenberg. Okay. So what happens is, if we take a look at QR iteration part of this, right? So I'm not going to refer to H as T because T is tri-diagonal. So if you look at T is equal to QR, and then T tilde is equal to RQ. Now, we are going to use shifts, as we recall from the regular QR algorithm, but I'll talk about shifts a little bit later. But I want to focus on this process because the point is you're still doing the same thing in that you're taking some matrix, shifted or not, QR factorizing it, and then multiplying the factors in reverse order. And if there is a shift, then you add a shift back. So what ends up happening is, because T is tri-diagonal, it's possible to show that R, which is known to be upper triangular, we can say more than that, is upper bidiagonal. So it only has non-zero entries on the diagonal and the first super diagonal. Everything else is zero. Another way of putting it, it has upper bandwidth of 1. And because of that, you then show that T tilde is also tri-diagonal. So that just as a Hessenberg structure is maintained when you do this QR and RQ, a tri-diagonal structure is maintained. And the way you can see that R is upper bidiagonal is if you I was paranoid about something here. Okay. Usually what I do when I do this in Teams and record it is I put a spotlight on myself. And I didn't this time, but I'm hoping that since no one else had their cameras on, that the me at the board will still be the dominant thing in the video. If not, sorry, Nemo. Okay, we'll see how that goes. Okay. Okay, yeah. So it's good enough. That's how it's showing for you, Dale. But sometimes the recording is different. And I guess I won't know about that until class is over. Okay, how you would see that R is upper bidiagonal is like if you do like what I've done other times here, where you use your X's to indicate non-zero entries. Like here in this 5x5 case, and see, well, okay, now I want to perform a rotation, row rotation to 0 on entry. So for instance, in this case, I want to rotate these 2 rows to 0 out this entry right here. Well, actually something seems strange here because wait a minute. That doesn't sound right.
Well, I mean, if R wasn't bidiagonal, then you would end up getting something in T outside of.
Yeah, it would, but okay, what's puzzling here is if I rotate these rows to QR factorized T, and I want to zero that entry, these two rows rotate and it gives me something up here. Okay, and then I rotate these two rows to make this zero. That'll give me something non-zero up here. So that's going to give me an upper bandwidth of 2, not 1. So now this is what my R looks like. But then, after I've done that, whatever given rotations I apply them left to make it upper triangular, and now I'm going to apply column rotations to on the right. So for instance, now I'm going to rotate the like before it's rotating the first two rows. And now I'm going to rotate in the same way the first two columns. Okay. And I can see how that's going to give me an entry here. Okay, and that's fine. And then I rotate columns 2 and 3. Which will put a non-zero back here. But how do I know that it puts a 0 back here? Now, the reason why I do know that is RQ. Well, R is equal to Q transpose T. And because T is symmetric and tridiagonal, this is symmetric too. So I can see how, just like in this unsymmetric case, if I do QR and RQ, I will get a Hessenberg matrix. I will introduce non-zeros down here again. And then because of the symmetry, these entries have to go away. But it looks like my statement about R being upper bidiagonal is off. Or does it would have upper bandwidth 2? Whoops. Well, now I gotta check that. If I make a matrix that is, I'm gonna go into MATLAB here, make a matrix that is symmetric. Whoops. Got that wrong. Try L. -1. Okay, now symmetric and tridiagonal. And then yeah, R has upper bandwidth 2, not 1. Dang it. Okay. Well, good thing I looked into that. Now I can make a correction in the notes. Okay. Okay, so we still preserve tridiagonal form by the symmetry, but okay, so set that up wrong again. Where I got that from? Okay. All right. Now, before what I can say about this QR-RQ process. Okay. Now, because of a tridiagonal structure, each Gibbons rotation of 2 rows or 2 columns affects only order 1 entries. So that means that total expense of doing QR and RQ is order n. Now, in the unsymmetric case, we were happy that the expenses process was order n squared because the matrix involved was Hessenberg. But now we can do better still because of the low bandwidth, even if it's not as low as I thought. Okay. All right. Although I should point out, it's still incurring order n squared expense if you are accumulating transformations, like you're saving a product of your Gibbons rotations. And that's something that you have to do if you are wanting the eigenvectors as well as the eigenvalues. Okay. So so unfortunately still have that to deal with. All right. All right, now we'll take a look at what is different as far as shifts. And we had a lot of work to do in the unsymmetric case. We had the single shift strategy, double shift strategy, double implicit shift, all that. Things are a lot nicer in the symmetric case. We still have the implicit cube here. But I would say it's not as vital in this case. So it means it basically uniqueness as far as the tridiagonal reduction. If you have two reductions of a matrix to tridiagonal form that both have the same first column, then they're essentially the same transformation. Okay. So that just generalizes in the most straightforward way. That's one thing. Also, you don't need to perform double shifts. Why? Because we only were doing that in the case of complex eigenvalues. Well, eigenvalues of symmetric matrix are real, so a single shift strategy is enough. Now, but what about the single shift case? In an unsymmetric case, we use the NN entry as a shift. We could do that here, just using the NN element of T, but it turns out in a symmetric case, we can do better. We use what is called the Wilkinson shift. Wilkinson was one of the biggest experts, maybe the biggest expert on the matrix eigenvalue problem. His famous book, the algebraic eigenvalue problem, like I said, it's all the secrets of how to compute eigenvalues efficiently. And I'm only really showing you tip of the iceberg here. So what is the Wilkinson shift? That is the eigenvalue of the lower right 2x2 block okay, that is closest to PNN. And so that's something that's easy to compute. Now I have a formula for it from the notes, as it written as a correction to PNN. So I have that where D is defined to be the difference of a diagonal entries over 2. Okay. Now, this is the wrong formula though. It is a correct formula. It is the eigenvalue of that matrix is closest to T and N, but it's not the best formula to use in practice. And just me off, I didn't use a better formula in the book, but I'll show you what it is here. Because let's suppose that this entry Tn n-1 is small. So that would mean that this square root is approximately the absolute value of D. So then you multiply that by sine of D. So this whole expression is approximately D itself. So when you have D minus approximately D, that's catastrophic cancellation. You're subtracting two numbers that are close to each other. So it's better to rewrite this using like the other quadratic formula. So that would be, so we'd have D plus sine of D. So now we have an addition down below instead of subtraction. And then we'll have a minus here, and then we'll have T n n-1 squared. So this is the safer formula in terms of floating point arithmetic. I mentioned before with the unsymmetric case, when we use this single shift strategy, that subdiagonal entry, but you wanted to go to 0, it would go to 0 quadratically. When we use a Wilkinson shift, a symmetric case, this is our unwanted subdiagonal entry. This goes to 0 cubically. So not only are our QR iterations cheaper, we need fewer of them that we're converging to diagonal form much more rapidly than in the general unsymmetric case. So other than that, we run the QR algorithm as is. Then I can comment on the expense. So a QR step. So that's a single iteration of this process, where you do QR factorizations, multiply factors in reverse order, deal with the shift. Takes 30 n plots if you are only after the eigenvalues. So that's a whole order of magnitude less than in the unsymmetric case. Okay, but it's for eigenvalues only. If you want eigenvectors as well, then you have this quadratic expense. But still, that's better. I think it was like 10 n squared in the unsymmetric case for the same thing. If you wanted to go to a real short form, that'll be the entire real short form. Okay, so that's a single QR step. The overall process of the QR algorithm in a symmetric case is okay. So 4/3 n cubed. In case of eigenvalues only. That's a huge difference from the unsymmetric case, which requires, I think it was like 10n cubed or something like that. Okay, and then and the main expense of this is not even the QR steps, it's the prime diagonal reduction that makes it take that long. And then you will add on 8n cubed if you want the eigenvectors too. Whereas the unsymmetric case, you have to add on 15n cubed operations just to get the rest of a real short form. And then you still didn't have the eigenvectors, there'd be more work involved to get those that I didn't talk about. So gotta love symmetry. It makes sense, like for instance, we're doing Gauss elimination, 2/3 n cubed operations, but if you had a symmetric positive definite matrix and you were doing LDLT or Cholesky, you were incurring half as many operations. But here we gain even more than that. So you expect to cut the number of flops by half because of symmetry, but here we cut it by even more. Like especially in this case, because we also have the favorable shift that leads to getting convergence in fewer iterations. We see what a big difference that makes. Okay. So that's what happens with QR algorithm in a symmetric case. So some point soon, I have some hints out there for the coding assignment for those of you who want to do that. So I know of at least a couple of you who do. And then, but next time, I'm going to finally tell you, after bringing up the SV singular value composition before, the SVD, how we actually compute it. And it's related, very closely related to the symmetric QR algorithm. Think of it as an optimization of that, specifically for SVD. All right, so are there any questions about anything? Alrighty, yep, you all have a good weekend too.